Greetings and welcome to this installment of the material science problems, and this one's about polymer crystallinity, and we have given to us that we are looking at the crystallinity of a polytetrafluoroethylene sample. Of course, PTFE is also known as Teflon. We are also given that the density of the sample, which can be relatively easy to determine, and that's usually measured in grams per cubic centimeter. We have two samples, and one has a density of 2.144 grams per cubic centimeter, and another one has 2.215. And we also can tell that the percent crystallinity of each is 51.3% for A and 74.2% for B. What we want to determine is the density of pure crystalline PTFE and also the density of pure amorphous PTFE. We have two samples, and usually when we have two samples in a problem like this, it means that we need to use both of these in the same equation to find our two unknowns. And this case is exactly like that. Our equation that we're going to use is the percent crystallinity equation. So for a sample, crystallinity percent is equal to the density of a purely crystalline form times the density of the sample minus the density of a purely amorphous form, all divided by the density of the sample times the density of a crystalline form minus the density of the amorphous form. This is essentially equivalent to the mass of all the crystalline form divided by the total mass, so the mass of the sample. And how this gets to this is the subject of a complete other video, as it does pose a number of difficulties. Well, we are going to start with just this section of it, and we want to solve for the density of the crystalline form right here. So we're going to solve this equation for that. So we're going to actually divide both sides through by the denominator here. So end up with this. And then divide through by this portion. and then multiply this portion out. Okay, so we need to find a way of getting this over to the other side, and for that we simply subtract this term from both sides. And we have density of C times this stuff minus the crystallinity percent times the density of the sample times the density of the crystalline form. And that all equals negative times the crystallinity percent times the density of the sample times the density of the amorphous form. Now we can separate out this from both of the terms on the left side, but also we're going to multiply through by -1 so that this becomes negative, this becomes positive, and this becomes positive. So to that end, take rho C times C percent density of the sample minus all equals this bunch. Okay, let's take care of some of this in here. Okay. Okay, we can combine these two terms. So it just becomes C percent minus 1. Then I'm going to divide both sides through by this term. So we can finally end up with an expression for the density of the crystalline form. Okay, this is all very well and good, but we have for either one of these samples, we have the crystallinity percent, we have the density of the sample, but we still don't have the density of the amorphous material. So what we can do is we can make one side A and set it equal to the exact same thing And we can use that to describe sample B. Sorry about labeling it A, might get confused with the amorphous, but it should be okay. We'll just plug the numbers from A here in there, and from B, plug those numbers in here. And we'll start that up at this side. So, C%, the crystallinity percent for A is 51.3. I'll just write the decimal in. Multiplied by the density of the sample, which is 2.144 grams per cubic centimeter. All that is divided by the density of the sample again, times 0.513 minus 1, and then I'm going to add to that the density of A. Forgot to put that up there. Okay, then we'll set this equal to the crystallinity percent of B times the density of sample B and that has to be multiplied by the density of the amorphous, and we'll divide all that by 2.215 grams per cubic centimeter. Multiply that by the crystallinity percent, and add to that the density of the amorphous material. Now we can cancel out this from here if we divide both by the density of the amorphous material. So we'll do some calculations and figure out what we have up here and have up here. At the top, we have 1.0999 grams per cubic centimeter, and divide that all by minus 1.0441 grams per cubic centimeter plus the density of the amorphous material. Set that equal to 1.6435 grams per cubic centimeter all over negative 0.5715 grams per cubic centimeter plus the density of the amorphous material. If I take both of these and raise them to the minus 1, just take their inverse, we can simplify our work. So I have this minus 1.0441 4, 4, 1. So there's the denominator, and here's the former numerator. Okay, now we can just multiply through, and we will get 6, 4, 3, 5 density of the amorphous 1.61 grams per cubic centimeter. Set that equal to 1.999 density of the amorphous minus 6.85 grams per cubic centimeter. And then, combining terms, I can subtract add these terms here. Obviously we get 0 here and 0 there. And over here we end up with 0.5436 times the density of the amorphous. That ends up equaling 1.0876 grams per cubic centimeter. Finally, dividing through by 0.5436, we get that the density of the amorphous is equal to 2.000 grams per cubic centimeter. Now that we have that, we can take this relationship and bring it over. So the density of the crystalline is, we can use either percentage, C percent, in fact, we can use what we have right here, did all the calculations except this. So cubic centimeter over plus this 2. And going through these calculations, we can determine that the density of the crystalline form is 2.301 grams per cubic centimeter. Okay. All right, that's the hard part. The next question, which is easy, is what is the percent crystallinity of a sample of the same type of polymer when that density of the sample is 2.26 grams per cubic centimeter. And we just need to plug that into our original equation right here. We know all of these parameters, so rewrite the equation here. Density crystalline minus density of the amorphous. Use our newfound values. Grams per cubic centimeter. All that gets divided by 2.26 grams per cubic centimeter. 2.301. And together ends up to be 87.95%. Depending on your significant digits, this value might vary just a bit, but that is what we're looking for. To sum up, we use two sets of experimental data, and knowing our formula for percent crystallinity, we were able to create an expression for the density of the crystalline component, and we used that twice, plugged these values in to those expressions, set them equal to each other. After much labor, we solved for the density of the amorphous component and then went back and solved for the density of the crystalline component. Using those values, plug them back into this formula to find the crystalline percentage of a completely different sample. And therefore we could find the crystallinity percentage of any sample now that we have these two values.